So when you look at the development of a morphine-morphinium chloride buffer, we look up the pKb at 6.13. We use the basic form of the Henderson-Hasselbalch equation, slap the numbers in and solve for the pH. I find this so much faster than the ice chart. So we get the pOH at 6.13 plus the log of 1.5. So that is equal to 6.31. The pH is 14 pKw minus 6.31 is 7.69. So now that's the easier part. Now the hard part comes. What happens after we dump in the sodium hydroxide? Well, the original amount of base was 0.5 molar and we had 1 liter, so we had 0.500 moles. Now when you're doing this, your significant figures becomes important. So put in those trailing zeros. We're adding hydroxide, so it uses up the BH plus and it makes B. My BH plus to start, I had 0.75 moles per liter times 1 liter, so I have 0.750 moles of BH plus to start. I added in 10 mils of 1 molar, 1 mole per 1,000 mils, so I added 0.0100 moles of hydroxide. That is BH plus that I used up, and it's equal to the amount of B that I made. So my base, I started off with 0.5 moles. I added 0.01 moles, so I have 0.510 moles of base in my beaker now. My BH plus, I had 0.750 moles. I used up 0.01 moles, so I now have 0.740 moles. Now, as I was going around the room, I did see one group that had these backwards. So it's important to stop and really think about what's getting used up and what's getting produced each time you do a problem. So my pOH is 6.13 plus the log of my BH plus, which is now 0.740 moles divided by 0.510 moles. Now, when you think about this, you could have turned this into molar, saying these moles divided by the total volume, 1.01 liters. But you're dividing them both by the same thing, so this is faster. So we get a pH of 7.71. So did that buffer do its job? Sure it did. Did we see a shift in pH? Yes. But was it a huge shift like we would have seen if we dumped that in an unbuffered system of water? No, not at all.